Okay, so the video that you watched before talked a little bit about how to figure out whether the reaction was going in one direction or the other. Now what I'm going to do is I'm going to show you different problem types, different ways that you can use all of this information to calculate either K or a concentration or something else. So if you know K, you can actually calculate the equilibrium concentrations from the what they will be at equilibrium from their initial concentration. And it's just a lot like stoichiometry. So we're going to talk through that. This is problem type 1. So it says, consider the information given and decide which way the reaction will go to equilibrium. So calculate the Q if necessary. And so if only the initial concentrations are given, the reaction obviously has to proceed to the right or in the forward direction. Because if we don't have any products, then obviously our reaction has to go forward to create those products. Now, this is a really important piece of information. You're going to construct an ICE table. Now, ICE tables are really, 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 really important in the equilibrium process. So if you don't understand an ICE table, please make sure that you stop us and talk to us about that. But an ICE table, see, ICE stands for initial, change, and equilibrium. And so what that tells us is we're going to set up a table to figure out the initial concentrations, the change in the concentrations, and then what the concentrations are going to be at the equilibrium. The first thing you need to do is write out the balanced chemical equation. So for this reaction, they actually gave it to us, and that is H2 gas plus I2 gas and double arrow 2HI gas. And so then you're going to set up your chart, and you're going to set up your chart given the information that they gave you in the problem. So you set up, you put ICE on the left-hand side, and then it tells you here, and the ICE tables can only either be in concentration or pressure. That is the only way that we can deal with ICE tables. You cannot put moles in the ICE tables. You have to put either concentration or pressure in the ICE table. So in this case, they give it to us in pressure. So this is 2.50 ATMs of H2 and 2.50 ATMs of I2, and we have none of the HI. So we know right away, we don't have to calculate a Q to figure out which direction the reaction is going to go, because guess what? We don't have any HI. We got to create that. So it's got to go in the forward direction. Now, this is where we use stoichiometry, and we follow along and we say, okay, I'm going to lose minus X of this. Because there is a 1 here, an understood 1 here, and an understood 1 here, these would be minus X. Now, because this is a 2 here, we're going to gain twice as many moles or whatever of HI as we lose of I2 or H2. And that's where these X's come from. So this is stoichiometrically why we get these X's and why we get the 2X, because of the balanced chemical equation. Then we're going to write what it is going to be at equilibrium. And that's just kind of rewriting what we've got here, 2.50 minus X. This one is also going to be 2.50 minus X. This one is going to be 2X. Now, it asks you to write an equilibrium expression. So we always do K, and in this case, it's Kp because we are using pressures. Kp is the pressure of Hi squared over the pressure of H2 times the pressure of I2. And these are all at equilibrium. So we're going to plug in, what do we know the pressure of Hi is going to be at equilibrium? It's going to be 2X. So 2X squared over 2.50 minus X times 2.50 minus X. Both of these are raised to the first power because there's only one of them in here and here. Okay, so what you're going to find now that's really awesome and really cool is that the top part of this and the bottom part of this are both perfect squares. It doesn't always happen like that. I'll show you a version that it does. But in this case, it does happen that way. And so that is really an awesome thing for us. And we also know that the Kp, because it told it to us in the problem, is 55.5. So if we take that equal to 55.5, and then we take and we do the square root of this side and the square root of this side, we can solve the problem. So what we can do to solve the problem is you calculate what the square root of 55.5 is. You then can rewrite the equation 2x over 2.50 minus x equals the square root of 55.5. Now, one thing that then you can do is then you solve, so you multiply 2.50 minus x times the square root of 55.5, and then combine like terms, and you should get your final answer. So in this one, you're going to then, so that is going to, my bad, that is going to wind up being 7.45, that is the square root of 55.5, times 2.50 minus x. And that is going to equal, so I'm going to multiply that up there, and that's going to equal 2x. And then when you do the multiplication here of that, let's see if we can get rid of this guy. If you do the multiplication of that, you get 18.63 minus 7.45x equals 2x. Now you got to move this over to this side so that the x's are together, and then we wind up, or you move this over there, and you wind, or just kidding, you do it the first way that I said, which is that you move this 7.45, add it to both sides, and you get 18.63 equals 9.45x. Come on. And so when you get 9.45x, you divide both sides by 9.45, and you get that x equals 1.97. Now, what the heck do you do with that step afterwards? So all you've done is you've solved for x here, and that's what it tells you to do. So to review, we figured out which direction it was going to go. We set up an ICE table. We plugged that ICE table, all that information, into an equilibrium expression that we are now able to write, and then we solved for x. Now, we're not finished with the problem because none of these over here are x, and it asks me to figure out the different partial pressure. So now what you've got to do is the last step here is you've got to take this x and you plug it in to all of these to figure out our pressure. So that's what the next slide says. The next slide, you take 2.5 minus 1.97, bam, and that's the pressure of H2 and it's the pressure of I2 because they're both the same. You take 1.97 and you square it, or not square it, excuse me, multiply by 2, and then you get the 3.94. Those are the pressures that you have. Now, to double check your work, it's always really important for you to double check your work. If you plug that back into the equation, you get 55.3, which is approximately 55.5 with all of our rounding errors, so you're good to go. That is the first and easiest type of problem that you can do. Now, if we deal with problem type number 2, if you know the equilibrium values, you can calculate K. So in this case, we are going to do it in terms of figuring out the equation and figuring out the pressures of this. So the first thing you need to do is set up an ICE table. So if you can set up an ICE table right now, pause your work and then come back to this. I will have the ICE table all set up for you. So now what you see here is that you see that the ICE table is set up for you. Hopefully you were able to come up with the ICE table. So you know that the 1.60 goes with the NO, that you wrote the balanced chemical equation. You notice that the I. Now, here's the kicker. Here's the really different part about this problem, is that you don't necessarily have to know the change and the equilibrium, because what it tells you is that the equilibrium pressure of NOBR is supposed to be 0.53. So in the blue is all the stuff that actually they told us this in the problem. So we know that the reaction is going to go in the forward direction. And they told us this part of the reaction. So what we have to do is we have to work backwards. And so we know that if this is a plus 2x, what we know here is that 2x is 0.53. To go from here to here, we added 2x. So if 2x equals 0.53, you could then solve for what is x. Divide by 2, and you've got that x equals 0.27. Then you can say, okay, if I have 1.60 here, and I'm going to lose 2x, this is minus 2x here. If I'm going to lose 2x, then I know that this is my equilibrium. So we're kind of working backwards on this ICE table. Now, I would recommend that you start the ICE table, you do this part where you show minus 2x minus x and plus 2x. So you know what the heck's going on with your numbers. But this right here tells us, hey, it's kind of a gift. We went from 0 to 0.53, and I know that I was supposed to gain 2x. So 2x is 0.53, and that's really nice. So hopefully that gives you some information about the first two problems. I'm going to make one more video about the really tricky problem and then some extra for fun, some extra practice for fun. But this hopefully covers most, if not most of the times that we are dealing with the different problems and hopefully it helps you figure out how to set up an ICE table. So